Welcome back, everybody. Today we're going to get going on Chapter 8, which is all about right triangles. And the first thing we're going to talk about in 8.1 is the Pythagorean Theorem and its converse. The objective today is to use the Pythagorean Theorem and its converse. Here we go. Alright, so now when I say Pythagorean Theorem, hopefully you're thinking good old a squared plus b squared equals c squared. Now, as far as what that means, if triangle ABC is a right triangle, so if we have a right triangle, then one of the legs squared plus the other leg squared is equal to the hypotenuse squared. Okay, or a squared plus b squared equals c squared. Okay, where a and b are the two legs of the triangles, the two non-hypotenuse sides, and c is the hypotenuse, the longest side of the triangle across from the right angle. Okay, that's our a squared plus b squared equals c squared. Now, as far as proving the Pythagorean theorem for you, there's hundreds of different ways I could do it. Here's my favorite. Let's say I have a triangle, and this triangle is going to be adjustable. I can change its angles. I can, if it lets me grab it, increase, decrease its size. Okay, so what I have here is basically all possible triangles with any angles, any sizes. And then what the squares are is they're meant to represent a squared, b squared, and c squared. Okay, so if this triangle has a side length of a, and I make a square with side lengths of a, we'd say that this area is a squared here. Okay, so same thing with b squared, same thing with c squared. What I want to show you here is that when I take a squared and b squared apart and put them together, I should end up with c squared. Okay, so I can do that by rearranging the chunks of b around the triangle here. And again, I can adjust my size here, so this is going to work with no matter what right triangle I look at. And I should be able to put the b squared around the outside. The a squared will fit in the middle. Yep, it's equal to c squared. Okay, again, that's going to hold true for different sizes of triangles here. Okay, so there you go. Pythagorean theorem works. A squared plus b squared is equal to c squared. So let's go ahead and show you how to use the Pythagorean theorem. Problem 1 says, what's the length of the hypotenuse of triangle ABC? So we want to figure out the length of the hypotenuse across from the right angle. We'll call that x for now. And what we're going to see here is that anytime I have a right triangle and I know 2 out of the 3 sides, I can find that missing side using Pythagorean theorem. Okay, so Pythagorean theorem, we said it was a squared plus b squared equals c squared. Leg squared plus leg squared equals hypotenuse squared. Let's fill that in with what we know. I like to start with the hypotenuse just to make sure I get that in the right spot. X is my hypotenuse, so on the right side we'll say x squared instead of c squared. And then for the a and the b, the 20 and the 21, it doesn't matter which one we think of as a, which one we think of as b. The legs don't have to be in a certain order. I'm going to say 20 squared plus 21 squared, but if you flip that order around, you'd get the same answer. Okay, what am I going to do with this now? Well, I have a pretty simple equation that I can solve for x in. Okay, we can square things out on the left side. 20 squared is 400. All right, plus 21 squared is 441 is equal to x squared. We'll add these together. 400 plus 441 is going to give me an 841 is equal to x squared. And then to get the x by itself, to get rid of the squared, what I'm going to do is I'm going to square root both sides of the equation. Okay, because squaring and square rooting are opposite operations, they'll cancel each other out. Okay, usually you won't do this, but I'm going to have kind of like the square root and the square cancel out. That's going to leave me with just the x on the right side. And if I plug in square root 841 on my calculator, we get a 29. All right, so we're at 29 for the length of my hypotenuse. All right, part B is the same thing, finding the hypotenuse on a right triangle using Pythagorean theorem. Why don't you take a minute, pause the video, work through part B, and then hit play to check your answer. All right, so running through B, once again we want to find the length of the hypotenuse, we'll call that x. I can set this up as 8 squared plus 15 squared, leg squared plus leg squared equals the hypotenuse, the x squared. Okay, we can square things out on the left, and you could actually do kind of the next few steps in one step on the calculator, if you're comfortable with that. We'll show all the work here. 8 squared is 64. 15 squared is 225. So 64 plus 225 is equal to x squared. We can then add those together. 64 plus 225 is going to give me a 289 is equal to x squared. And then again, to get the x by itself, I will square root both sides of the equation, leaving me with just the x on the right, and on the left we get a 17. So I have a hypotenuse of length 17 for part B. All right, next up, problem 2. Still using Pythagorean Theorem to solve for parts of triangles. Okay, there'll be a few differences in this one. Okay, it says, what's the value of x? And express answer in simplest radical form. We'll explain what this means in just a minute. Let's get this problem going though. Now notice the first thing here is that I already know my hypotenuse. Okay, the x we're solving for is one of the legs of the triangle. So when I go to do my a squared plus b squared equals c squared for this one, the c, the hypotenuse, is going to be a 20. And the x is going to be one of my legs, so we can say x squared plus 8 squared on the left. One of the biggest mistakes I'll see from students doing Pythagorean Theorem is to always put the x in the c position. Okay, nope, the hypotenuse always goes in the c position. X will either be the c or the a or b, depending on if it's a leg or a hypotenuse. Okay, once again, we'll solve for x. I'm going to square things out. So we can say we have x squared plus 64 is equal to 400. I'm then going to subtract 64 from both sides of this equation to give me x squared is equal to 336. And then at this point, what we did last time is we took the square roots. We'll still do that. That's going to leave me with just x on the left. And then notice when I go square root 336 for this one, I don't get a nice answer. I get an 18.33030278, kind of a mess that's going to continue on and on repeating. Okay, so technically that's not the actual answer what I just wrote down there. It's an approximation. So what I might want to do is make some squiggly equal signs, whoops, to show that this is approximately my solution. Okay, but in certain cases, I don't want an approximation. I want the exact solution, which is this square root 336. That's where the simplest radical form is going to come into play. For simplest radical form, you're going to give the exact solution, but you're going to reduce down the answer as much as possible. We'll show you how to do that right now. So let's get rid of this approximation. Let's say x equals the square root of 336. Okay, so that's an exact answer. I want to reduce that to simplest radical form. We'll show you how to do that right now. Okay, to do that, what I'm going to need to do is break 336 down into a prime factorization. Okay, I want to break it down into its prime factors. And I can do that with a factor tree. Let's do that here. Now 336 is even, so I know it's divisible by 2. I'm just going to divide it by 2 right off the bat. Okay, when I divide by 2, I end up with a 168. So now that 336 is equal to 2 times 168. And I can break 168 down. I know it's even, so I'm going to divide that by 2. When I do that, I get 2 times 84. All right, 84 is even as well, so I'm going to divide by 2. We'll get 2 times 42. And my face is in the way. Let's just hide that, get that out of the way. There we go. 42 is even. We can go 2 times 21. And then 21 isn't even anymore. It is equal to 3 times 7, so I'm going to write 21 as 3 times 7. Okay, so why did I do that? Well, I just showed that 336 is equal to 2 times 2 times 2 times 2 times 3 times 7. Okay, we'd say that's a prime factorization of 336. All the multiples are all prime. And why am I doing that? Well, what I'm looking for is I'm looking for perfect squares. In other words, groups of 2 numbers at a time. So there's 2 2's here, so 2 times 2, in other words, 2 squared. And same thing with this other set of 2's, that's another 2 squared. So the way I'm going to rewrite this square root of 36 is I'm going to rewrite it as square root of 2 squared for my first set of 2 squareds, times 2 squared again for the second set of 2's, times just the individual 3, and times the individual 7. And the reason I want to do that is I know that the square root is going to cancel out anything squared. Just like my square root cancel out the x squared to be just an x here, same thing, the square root will cancel out the 2 squared. So what I can do is I can pull that 2 outside of the root. Same thing with this second 2 squared will cancel and pull out front. So what that's going to give me then is that x is equal to, out front, 2 times 2, with the regular 3 on the inside and the regular 7 on the inside. Okay, if it was squared, I'll pull it out. If it's not squared, we'll leave it in. And then what I can do is just multiply everything on the outside and everything on the inside together. On the outside, 2 times 2 is a 4. On the inside, 3 times 7 is 21. Okay, I'd say that 4 root 21 is my answer in simplest radical form. It's an exact answer. It's the same thing as the square root of 336. Okay, but we've pulled out all the perfect squares, which are going to make this answer a little bit nicer to work with. Okay, if we had to do some different things with it later. Okay, that's an example of reducing a radical, and that's actually a pretty ugly example for what we're going to throw at you for homework and the rest of the way here. Part B is the same idea. I want you to take a minute, pause the video, okay, work through that problem, use the Pythagorean Theorem, reduce that radical down, and then hit play to check your answer. All right, going through this one, we have our legs, 10 and x. So I'm going to say again, x squared plus 10 squared is equal to the hypotenuse, 16 squared. Squaring that out, we'll have x squared plus 10 squared, which is 100, is equal to 16 squared, which is 256. I want to get the x by itself, so I'm going to subtract 100 from both sides. That'll give me that x squared is equal to 156. And then at this point, what we'll do, since it says put the answer in simplest radical form, we'll square root both sides. We'll cross our fingers. Hopefully it works out nice. Square root 156. Nope, not a nice number. So what we need to do is just like we did in the last problem, factor this 156 down so we can put it in simplest radical form. Okay. 156, it is even, so I'm going to divide it by 2. And I end up with a 78. Okay, 78 is even as well, so I'll divide that by 2, and I end up with a 39. Okay, now 39, not even, so I can't divide by 2. I'm not sure what else I can divide this by. Let's try 3. Yep, it works. Okay, 39 is divisible by 3, and we get a 13. Okay, I know 13 is prime, and nothing divides into that, so we're good with our factoring. So what I can do then is I can rewrite the square root of 156 as, let's see, I'm seeing one group of 2's, so I can say it's the square root of 2 squared, okay, times a 3 times a 13. And when I square root something squared, it cancels, so I'll pull that 2 out front. That's going to leave me with x is equal to 2 times the square root of 3 times 13 on the inside, which is 39. All right, so 2 root 39 will be this answer in simplest radical form. All right, next thing we're going to take a look at are a couple of story problems utilizing Pythagorean Theorem. A lot of practical applications to Pythagorean Theorem because there's a lot of triangles in the real world. All right, so let's go through a few. First one, problem 3a says, Jamal leans a 12-foot long ladder against the side of a house. The base of the ladder is 4 feet from the house. To the nearest tenth of a foot, how high in the house does the ladder reach? Okay, so this sounds like something I had to figure out hanging Christmas lights a couple months ago. Picture would be nice. Let's draw it out. We have a sweet-looking house. And it says Jamal leans a 12-foot long ladder against the house. So that means we're going to have a ladder at an angle like this, which is 12 feet long. Okay, the base of the ladder is 4 feet from the house. Now, anytime you see this base word in a story problem, typically that's talking about a distance along the ground. So that's going to be this distance here from the base of the house to the base of the ladder, 4 feet. And then we want to know how high in the house does the ladder reach. Okay, so that's going to be this distance right here. We'll call that an x. And that's something we want to figure out to see, does our ladder reach the second story window? Is it going to reach the roof? All right, so there's our x. Okay, we can use Pythagorean theorem because we'll assume that this house comes out of the ground at a right angle. So we have a right triangle. We know the hypotenuse. We know one of the legs. We can use Pythagorean theorem to solve for the other leg. So I'm going to set up my a squared plus b squared equals c squared as, let's say, x squared plus 4 squared equals 12 squared. All right, let's square things out. So we have x squared plus 16 is equal to 12 squared, which is 144. We want to get the x by itself, so I'm going to subtract 16 on both sides. That'll give me that x squared is equal to 128. And then I'm going to take a square root on both sides, and I end up with x is equal to 11.3. And for this one, it asks to the nearest tenth of a foot. Okay, so in other words, round. All right, it's asking for a rounded solution, not simplest radical form. Okay, and typically your story problems you're going to look for rounded rather than radicals. Okay, that's an example of using the Pythagorean theorem in a story problem. Why don't you take a minute, pause the video, give part B a shot, and then hit play to check your answer. All right, running through part B, we have a guy wire is to be attached to the top of a 15-foot tall telephone pole. Let's start drawing that out. We have a telephone pole. We know it's 15 feet tall. And we're going to hook a wire to the top of it, like so. All right, if the wire is to be anchored to the ground at a point 4 feet from the base of the pole, so meaning that distance from base of the pole to the wire is 4 feet, we want to know how long does the wire need to be. In other words, wire's length is our x. We want to solve for that x there. Okay, again, Pythagorean theorem applies here because I have a right triangle. I know both the legs. We can use that to solve for the hypotenuse. So I can set this up as 15 squared plus 4 squared is equal to x squared. Okay, and I'm just going to plug the 15 squared plus the 4 squared in my calculator in one shot. It's going to give me a 241 is equal to x squared. And then when I take a square root on both sides, square root of 241 is just a 15.5, we could say. All right, so that's wire's length will be 15.5 feet long. All right, next thing we're going to look at is the converse of the Pythagorean theorem. Okay, another way we can use our a squared plus b squared equals c squared. And it says that if the sum of the squares of the lengths of the legs of a triangle is equal to the square of the length of the hypotenuse, then the triangle is a right triangle. Okay, so in other words, if we have a triangle with three side lengths a, b, and c, and we figure out that a squared plus b squared is equal to c squared, okay, well that means that my triangle is a right triangle. Okay, so what this gives us here is a way to check and see if we have right triangles. We can think of it as a right triangle test. Okay, along with that, we're going to real quick talk about the idea of a Pythagorean triple. I'm going to say that's a set of whole numbers, a, b, and c, such that a squared plus b squared equals c squared. Okay, so anytime you have a right triangle with whole numbers, okay, the a, the b, and the c that satisfy a squared plus b squared equals c squared will be a Pythagorean triple. So if we're checking to see whether or not triangles are right triangles or not, we're also checking to see if their lengths are Pythagorean triples. So let's go ahead and show you how to do that right triangle test. Let's say a triangle has side lengths of 85, 84, and 13. We want to know, is the triangle a right triangle? So what we'll do is we'll check a squared plus b squared. We'll also check c squared, and then compare them to each other. Okay, now for the a and the b, I need to use my smaller two sides. If this is a right triangle, the c, the hypotenuse, needs to be the largest side. So we'll do for the a and the b 84 squared plus 13 squared. Now I'm just going to plug that straight in my calculator. One step, I end up with 7,225. For the c squared, we'll use 85, so 85 squared, when I plug that in, is also equal to 7,225. So for this one, are these right triangles? We're able to say yes, because a squared plus b squared is equal to c squared. All right, part B, same idea. Pause the video, give part B a shot, and then hit play to check your answer. So in part B, we'll look at a squared plus b squared again. That'll be my two shorter sides, 16 and 48. So 16 squared plus 48 squared. When I plug that in, I end up with a 2,560. For a c squared then, that's going to be the longer side, the 50 squared, which is just 2,500. Okay, so these are close, off by just a little bit, but not quite there. So in this case, do we have a right triangle? I'd say no, because a squared plus b squared is not equal to my c squared. All right, now the last thing we're going to do today is extend on that converse of the Pythagorean theorem a little bit to classify triangles a little further. So our next theorem says that if the square of the lengths of the longest side of a triangle is greater than the squares of the lengths of the other two sides, then the triangle is an obtuse triangle. So in other words, if we have c squared is greater than a squared plus b squared, our triangle is going to be obtuse. Here's the reason for that. Let's say I have a right triangle here. With a right triangle, we know c squared equals a squared plus b squared. Now let's see what happens if I make my c a little bit bigger, so that c squared is greater than a squared plus b squared. Okay, what's going to have to happen to this right angle then, it's going to have to open up. It's going to have to turn into an obtuse angle to make that triangle work. So if c squared is greater than a squared plus b squared, our angle, our biggest angle, is going to be greater than a right angle, making it an obtuse triangle. Same idea with our next theorem. If the square of the length of the longest side of a triangle is less than the square of the lengths of the other two sides, then the triangle is acute. Again, in other words, if c squared is less than a squared plus b squared, that angle has to be less than a right angle. It has to be an acute angle. Okay, because again, for example, let's say I have a right triangle. We know that c squared is equal to a squared plus b squared. If I make that c shorter, okay, that right angle is going to have to get shorter. Now we have a acute triangle, okay, because that right angle has got to be smaller. All right, so kind of sum that up. If C is less than, our angle is less than a right angle, an acute angle. But if C is greater than, our angle will be greater than a right angle, so an obtuse angle. All right, so let's show you how to do that triangle classification here then. Problem 5, part A says a triangle has side lengths of 6, 11, and 14. We want to know, is it acute, obtuse, or right? Well, let's see. Let's take a look at a squared plus b squared, which would be 6 squared plus 11 squared, which is equal to 157. Let's look at c squared then. So the longer of the three sides, which will be 14 squared, that's equal to 196. Okay, so c squared is 196. A squared plus b squared is 157. So we just showed that c squared is greater than a squared plus b squared. All right, so if c squared is greater, that means that that angle's got to be bigger than a right angle. So we're looking at an obtuse triangle. All right, that's how our triangle classification works based on side lengths. Why don't you take a minute one more time, pause the video, work through part B, and then hit play to check your answer. All right, running through B, we've got our two shorter sides for a squared plus b squared. That's going to be 7 squared plus 8 squared, which is equal to 113. For c squared then, we'll use the biggest side, the 9 squared, which is equal to 81. Okay, in this case, we see that c squared is less than a squared plus b squared. Okay, therefore our kind of biggest angle has to be less than a right angle, meaning we have an acute triangle. All right, so that's it for lesson 8.1. Start going to town on the homework, start getting your practice in. Let us know if you need help, and we'll build off this stuff in the next lesson.